is obtained in this way, as in the middle equation, by operating this simple transformation. And so we can define the variable or the integral associated with the derivative, which actually, thanks to the theory of generalized fractional operators, perform the inversion of the derivative in this way. But also in this case, the kernel is not known in explicit form, but is just known as the Laplace transform inverse of this function. And then, it is necessary to consider that there are some conditions in order to ensure the existence of the Laplace transform of the two kernels. We cannot choose any kind of kernel, or better, we cannot choose any kind of transition function alpha of t. But in order to the two kernels, the kernel of the derivative, the kernel of the integral, are actually the Laplace transform of some function. The limit for the spectral variable to infinity must be 0, and these conditions are satisfied if the Laplace transform of the transition function satisfies this condition, and thanks to the finite value theorem, the initial value theorem of the Laplace transform, we have that a necessary condition for the existence of the Laplace transform of the kernels is that the limit for t tending to 0 must be strictly in the interval between 0 and 1. This is an important condition which basically confirms that the operator must be singular at the origin. Cannot be very regular at the origin, not be 0 or 1. But as you can see, once we know the Laplace transform of the transition function, we have to compute in some way the variable order kernels in the time domain. We don't have any analytical representation, as we have already mentioned, and we have to numerically invert this Laplace transform. In this work, we have just considered a quite standard method, a modified Talbot method, as described by Wildman and Jeffan in 2007. I will give a short description. By means of the formula for the numerical inversion of the Laplace transform, we write the kernel of the derivative, but the same as for the kernel of the integral, in this way, as the integral of the Bromovich line. Usually, we have to identify the region of convergence, which clearly cannot be identified in a priori way, but usually depends on the transition function. So the analysis must be tailored for any transition function, for any value of the function of alpha of t. And how it is performed, the numerical inversion of the Laplace transform. There are two main steps. The first one is that the Bromovich line is deformed in a contour starting and ending in the left outer plane, in the left part of the compressed plane. This is necessary in order to avoid the strong oscillation of the exponential here, which would create catastrophic stability. And then we apply some quadrature rule on a truncation of this contour. Since we have deformed the contour in a way that it ends in the left outer part of the convex plane, we know that the exponential ensures a fast decay of the integrand, and then we can truncate. And given certain tolerance, we can select both the contour and the parameters of the quadrature rule in order to achieve the required accuracy. For instance, but it is just an example, we can consider a very simple parabolic contour. worked several times on parabolic contour. They are very simple because they basically depend on just one parameter. So it is very easy to perform an error analysis in order to find optimal parameters. And thanks to this contour, we transform this integral in the complex plane in a line integral by means of this function. So you can apply, for instance, a triplet trapezoidal rule. We prefer to use very simple rules because the parameters must be identified by means of the error analysis. So also the error analysis must be very simple, otherwise it's very difficult to find optimal parameters. And the main parameters of the rule, the trapezoidal rule, the step size h, and the number of nodes n, together with the shape of the contour move, are obtained by means a balancing of the three different components of the error: discretization error, truncation error, and dot error. I'm skipping on all the technical details because my aim is to just give main ideas in this topic. However, these estimations were found for the first time by Weidemann, who incorporated the Randolph error in this analysis. The Randolph error is important because if the parabola becomes very large, the exponential can involve a large error. So it is necessary to keep under control also the Randolph error. So let's see some examples of application. We first consider a transition order in which the equation starts from an order alpha 1 and goes asymptotically to an order alpha t by means of a parameter c, which in some sense describes the speed in which this transition happens. We think that in applications, usually alpha 1, alpha 2 should be quite close, but just for convenience, we have considered quite far values to show that the difference. So here is a plot of the kernel obtained as the inverse Laplace transform of this function, which is the function that we need to define the derivative. As you can see, this kernel matches the kernel of the derivative of constant order alpha 1 in the starting phase and match the kernel of the constant fractional derivative of order alpha 2 in the final case. Maybe this can be in a clear way, can be seen in a clear way in the logarithmic scale, where you can see there is a perfect match with the initial value of the order and the final value of the order. The same happens with the kernel of the integral. Also, in this case, we have a match of the two constant order. The constant order alpha 1 in the first phase, and the constant order alpha 2 in the final case. Usually, we can consider any kind of transition function, which satisfies the condition that we have seen before. But in our idea, too much convoluted function does not make sense from a physical point of view. But in any case, it depends on the problem. Here is an example, very simple example, related to a relaxation equation with exponential transition. In our paper, you can find some other exact example of a transition function. Here we present just this exponential transition. We can compute the exact solution here directly by means of inversion of Laplace transform. Also, in this case, we have compared the solution obtained in this variable order framework with the solution that we will have obtained if we use the constant order alpha 1 and constant order alpha 2. Also, in this case, we can see the match in the initial phase with the constant order alpha 1 and the final case with the constant order alpha 2. Okay, we can conclude by just showing some other aspects that we can consider. For example, higher order transition in the interval n-1 n. Here we have to make some changes in the kernel because we have a kernel of a higher dimension, but also in this case we underline the importance of alpha 0. It is interesting to study operators of variable order with respect to space, and in particular, for our point of view, this is mainly a community of people working on numerical methods, to derive reliable numerical methods for solving the differential equation with alpha, with this variable order derivative. Obviously, the first idea is to think to Lubig's convolution quadrature rules, which requires the knowledge of the Laplace transform of the kernel and not of the kernel itself. Here is a list of some of the references which are here given before.
Okay, so first of all, we thank Roberto for the presentation.
I have to read the question.
Okay, are there questions from here? And then we read there's a long question from Kai Beaton.
Okay, the question is quite long. I can summarize. The mainly concern is from Kai Dieter. Yes, thank you, Kai, for attending this presentation. He asked about the possibility of a semi-group property. In particular, yes, this. If we consider the integral alpha, the integral variable order alpha t, and the integral variable order beta t, they commute. Actually, integral of alpha t applied to integral of beta t is equal to integral of order beta t applied to integral over alpha t, and it is equal to integral of order alpha t plus beta t. These results. This result came from the Luchko theory of generalized fractional order. About the concatenation, he also asked about the concatenation of derivative of different variable order. I think that this is an open question. In particular, it's an open question to identify the class of function which satisfies this property, but also to clearly identify the class of function for which this theory is holds. For this theory holds is not a completely defined. It's not a completely closed problem. I just give a necessary condition, but not a sufficient condition. So I think there is still something to work on.
Okay, we have time. So thank you, Roberto, again. Okay, so the next speaker is Andrea Giusti from ETH in Zurich. He will talk about fractional Newtonian gravity and galactic dynamics.
Madonna.
It's okay, Robert?
Come mostro tutto con
L.
Oh.
Okay, thank you, Andrea.
Per cambiare le slides.
Avanti,
Okay, so
First of all, I must admit that it's pretty hard task to speak after Roberto and Martin, and I hope to be up to the task. The basic idea behind. All right. Okay.
Ora stavo guardando un commento che è
Okay, let me go ahead then. Okay, the key idea behind this presentation is to introduce you to a sort of new perspective on the typical phenomenology which is typically associated to dark matter, and based on a fully fractional theory. Okay, so let me start off by reviewing some results concerning galaxy rotation curves for discrete galaxies. And specifically, if we were to live in a perfectly Newtonian universe, we could plot the orbital speed of stars moving around the galactic center as a function of the distance from the center, and we would get this dashed line, which is exactly the standard Newtonian prediction for this sort of curves. However, if we look at astronomical data, we get something which is extremely different, that diverges a lot from the standard Newtonian description. Specifically, we get that at large scales, very far away from the galactic center, the orbital velocities of stars tend to flatten out. And this can actually be explained from a theoretical framework in two different ways, very different ways actually. We either have to assume the existence of an exotic form of matter that we typically call dark matter, which is supposed to have no direct interaction with the electromagnetic sector and to contribute an almost negligible pressure to cosmological models. And for this sort of stuff, we have a series of proposals ranging from primordial black holes coming from the early universe, or even particles from beyond the standard model of particle or beyond the standard model of particle physics. Or we have to assume that gravity gets modified, gets weird at some large scales at the astrophysical level. And this is actually the key idea behind the empirical law, the empirical model known as Milgrom's modifying Newtonian dynamics, which is known as MOND for short, which is supposed to be an effective theory at low energy and low speeds, which should emerge from a more fundamental theory of gravity, which can be either a modification of Einstein gravity or even an effect coming from pure quantum gravity models. And honestly, and this is my personal perspective on the problem, since we have no direct evidence of any deviation of particle physics or of any physics beyond the standard model of particle physics coming from the Large Hadron Collider, I have decided to focus on the second option, namely on modifying gravity at large scales and relating these sort of things to quantum effects to gravity. Okay, so let me therefore review this empirical model originally proposed by Milgrom, according to which we have that there should exist a critical acceleration scale A0, above which we simply recover the standard Newtonian dynamics, whereas when we fall below this threshold A0, we get a modified dynamics for our test particles. And this behavior basically implies that for short distances, we recover at least short astrophysical distances, we recover the standard Newtonian description of the orbital velocities, whereas as we move away from the galactic center and as we approach the outer region of a galaxy, of a spiral galaxy typically, we get a flattening of our galaxy rotation curves. And this actually reproduces the empirical Tully-Fisher relation for spiral galaxies that basically relate the intrinsic luminosity of a spiral galaxy with its rotational velocity. Okay, but now, and of course, we all know that Newton's gravity can be thought of as a field theory, a classical field theory based on the Poisson equation, which basically leads to a linear theory. And similarly, MOND can be thought of in terms of a field equation, which is ultimately nonlinear and based on modification of this Poisson equation originally proposed by Bekenstein and Milgrom, where mu here is nothing but an interpolating function aimed at reproducing the two asymptotic behavior that we've seen in our empirical description of the model. Okay, so but now, why should we even bother to look into fractional effect for galaxies or for this sort of a phenomena? Well, let's be honest, non-local effects in the quantum field theory are not something really new, because after all, if we take massive electrodynamics and therefore we provide a sort of Lagrangian for the massive photon, as we typically do sometimes in quantum field theory, which is given by the proper Lagrangian here, which is clearly breaks explicitly the gauge invariance, it turns out that this Lagrangian is dynamically equivalent to this non-local Lagrangian here, which is instead gauge invariant. And somehow we are hiding the additional propagating degrees of freedom that emerges from this description into the non-locality of this action, where 1 over box is a nasty physicist way of representing the convolution between the green function of the D'Alembert operator and whatever lays on its right-hand side. But let's move on to gravity. And it turns out that fractional stuff, when it comes to quantum gravity or effective field theory description of gravity, are not really something new. Indeed, it turns out that there exists a unique class of ghost-free linearized theory for a spin-2 field, which is a fancy way of calling the graviton, that together with some technical assumption, lead to a modification of Newton's dynamic at a certain crossover scale, which can be macroscopic. And the general form of the Lagrangian for this theory is given by this expression here, where m squared is a mass-like term that to the leading order depends to the alpha power of the D'Alembert operator. And of course, within this sort of approaches, alpha is constrained to be between 0 and 1, and specifically for the Vali-Gavadadze-Quarrati model is exactly 1/2. Okay, but as you can imagine, the idea behind fractional Newtonian gravity was I tried to propose last year and then developed with Roberto later on the same year, is based on a simple modification of the fractional Boston equation by replacing the standard Laplacian with the fractional one. And to do that, we basically used the spectral representation of the fractional Laplacian, which is given here. And in order to do that, it turns out that we had to include an additional length scale, L, for dimensional reason. And this length scale will be particularly important in the next 2 slides. Okay, but as a physicist, of course, I want to solve naively this sort of equations. And therefore, if I have something like that, I want to find an operator that basically inverts the Laplacian and gives me the answer whenever I give a source term to my equation together with some boundary condition at infinity. And this can actually be done rather easily in the Fourier space. Indeed, this is exactly the form of the solution, the general solution in the Fourier domain. But of course, this quantity here would not be a tempered distribution for s larger than 3/2, and therefore we have a constraint for s between 0 and 3/2, so that this whole story holds on. Okay, so if we use this constraint, then we can use the integral representation of the gamma function to provide an integral representation for the inverse fractional Laplacian for s between 0 and 3/2. And this is a general expression that you can find in probably most articles concerning the fractional Laplacian. Okay, then, so now we have the setup of our problem. We have our fractional Poisson equation for gravity, which is given by this expression here, and this is a general solution for this problem, assuming some certain behavior of infinity. And now we want to see what happens if we consider some specific mass density profiles. And the simplest one we can consider, for instance, is a point-like source, which is basically looking for the green function of our problem. And then we can try to move on to a more realistic scenario where we take, for example, the Casimir disk, which is a model for a very thin disk galaxy, and see what happens. Okay, let's start with the point-like source. We simply plug in the density profile, and we just need to recall that this quantity here, this operator here, generates the solution of the classical equation, and therefore the action of this operator here onto a function f is simply the convolution of the Gauss-Weierstrass kernel with the function f. And if we put together these two quantities and the definition and the integral representation for our fractional Laplacian, we immediately get that the action, the fractional Laplacian onto this Dirac delta yields simply a power law decay, which is simply given by this expression. And therefore, the general solution for the point-like source for S between 1 and 3, or at least 0 and 3 halves, is given by this expression here. And of course, one can check that if we take S to 1, we recover the standard Newtonian potential. But now it's natural to ask what happens if we take the limit for S approaching the upper limit of our boundary for S. And it is actually easy to see that this quantity diverges in that limit. But the problem is that in physics, we don't really care that much about the potential, but rather we care about the physical observable that typically depend on the gradient or the derivative of the potential. And it turns out that the gradient of this potential is always well defined in that limit. And therefore, it's natural to look for a sort of regularization of the integral that leads to this limiting behavior for our potential. And this can actually be done in a very simple way. We can take the spectral decomposition of the fractional Poisson equation in the limit for S equal to 3 halves, which is this sort of, which is given by this stuff here. And then we see that this integral has a logarithmic divergence, and using some regularization techniques, and this result is actually independent on the regularization method, yields a logarithmic potential. And therefore, we can now compute the physical observables that we are interested in, namely the acceleration and the orbital velocity, which are simply given by the standard Newtonian expressions. And these are the expression for the orbital velocities for our stars in the case of a point-like source. And again, for S equal to 1, we recover the standard Newtonian prediction. And for S equal to 3 halves, we recover the Tully-Fisher relation for spiral galaxies, provided that we choose S and we choose L to be equal to this quantity here. And therefore, we have found a constraint on these three parameters that we have at the beginning of our formulation of the model. Then this is a simple plot of the orbital speeds as a function of the distance. Now, let's move on to something a little bit more physical somehow, and let's look to for the case of a very thin disk galaxy. And this is actually typically described in terms of the Casimir disk, which is given by this matter density. Then we can simply compute all the quantities that we are interested in through the Fourier transform method, and this is the general solution that we find for our potential in terms of these two integrals. Now, if we focus on what happens away from outside the galactic plane, we can actually compute this integral numerically, and we can get these equipotential surfaces, or at least I trust Roberto, because this is exactly what he did at the numerical level, so if something doesn't work, it's his fault. Okay, instead if we focus on what happens on the galactic plane, which is exactly what we are interested in from a physical perspective, because we care about the motion of stars, and the stars in this model will lay on the galactic plane. We find these expressions for the potential for S between 1 or 0 and 3 halves, and for S equal to 3 halves. And again, we see that we can regularize the behavior of this potential in the limit for S approaching 3 halves, and we get this sort of logarithmic behavior plus a small correction. Then, if we take the derivative and compute the orbital speeds for visible stars on the galactic plane, we get these two quantities, and again, we get a correction to the flattening of galaxy rotation curve of the order of R0 over R, where R0 is basically tell us about how spread out is our galaxy with respect to the center. And this is a simple plot of the orbital velocities of stars as a function of the distance from the center. And where S varies from 1, which is the Newtonian prediction, up to 3 halves. And the key point here is that if we want to actually reproduce the full phenomenology of galactic dynamics, we need to make our model scale dependent. And how do we do that? We need to make the fractional Poisson equation a variable order problem, which is extremely difficult to handle. So what's next? Well, first of all, as I said, we need to make things variable order, and therefore we need to find the proper definition of variable order fractional Laplacian that fits this whole construct. And this is actually a very hard task from both an analytical and numerical perspective, also because we completely lose any sort of uniqueness results that instead we might have for the standard population. Furthermore, from a more physical perspective, we need to make sense of the theory at the variable order level, namely by formulating a sort of variable order fractional field theory that justifies our discussion. And in doing that, we will need to understand whether this variable order enters as a constraint to the theory or as a new degree of freedom. So to wrap up, the idea as installed basically was to offer a way to understand dark matter phenomenology as a result emerging from a fully fractional theory of gravity. And this fractional nature of the theory is inherently related to the non-local field theories. And we can actually provide a prediction for the typical scale at which this sort of non-local effects should emerge in astrophysics, and which is actually given by this expression right here. And of course, now, in order to make some observational prediction, we need to make everything scale dependent, and we are actually pretty close to it. So stay tuned for the next few weeks. And this is more or less it. Thank you very much for your attention.
Thank you, Andrea. Other questions? Other questions in chat?
No.
Okay, so
Thanks.
thank you, Andrea.
Cheers.
We are 5 minutes in advance. Should we wait?
Maybe it's better.
Okay, so
Maybe we have a questions from another galaxy.
okay, so we may stop for minutes and then.
Just 5 minutes of break in order to wait for the exact time in which is scheduled the next talk. Okay.
Vabbè, forse possiamo anche finché presenti.
Okay, so we continue now. The next speaker is Angela Cardone. She's from University of Salerno, and she will talk about the spline collocation method for fractional differential equations, theoretical and computational aspects. Thank you, Angela.
Thank you. Good morning, everybody, and thank you for attending this talk. I will present a joint work with Professor Diana Conte and Professor Beatrice Paternoster from University of Salerno. And I will speak about the numerical solution of an initial value problem where the derivative as a fractional index alpha, and it is evident from the definition or in the Caputo sense, and as it was already reminded today, the derivative depends on the past history of the solution. And for this reason, fractional differential equations are a powerful tool to describe many evolutionary problems with memory. And this is just an example in the context of viscoelastic materials. This is a model of the heat conduction in a viscoelastic material where it is applied a plane stress condition. In this case, we recover the classical model when alpha is equal to 1, while in the case alpha is less than 1, we have the fractional model. If we consider the classical model, some non-physical phenomena can be predicted, as for example, high oscillations of the temperature at the beginning of the interval, or even negative values of the temperature. And moreover, some other bad effects like not steady big values of the stress intensity factors. While those two effects disappear when the derivative is the fractional derivative is less than 1. This is only just an example. Many other applications can be considered, and some other were remembered today. And for this, and also great attention was paid to the numerical solution of fractional differential equations. Here I mentioned just some very popular methods, and among them I will focus on spline collocation methods. Sorry. Okay. Spline collocation methods. The motivations. This class of methods is very classical, and they were applied also to ordinary differential equations, to Volterra integral equations, because they can reach high order of convergence, they can have strong stability properties, and moreover, they provide a continuous approximation of the solution, in the sense that they give an approximation of the solution at each point of the time interval. And now I will illustrate the construction and analysis of a class of spline collocation methods to the fractional differential equations. In particular, before applying spline collocation methods, we have to derive an equivalent formulation of the initial value problem. And in particular, we will consider the equivalent formulation, that is the equation, the functional equation 2, which is a nonlinear equation where the unknown function z appears in on the left hand side, and on the right hand side under the sign of fractional integral. And once we have solved the equation 2, we can obtain the solution of the of the initial value problem 1 by this simple formula, that is, we have to compute the fractional integral of z plus function q. So now our intent is to solve the equation 2. And by collocation, we approximate the function z by piecewise polynomial of degree m. The first class of methods, they are the one-step spline collocation methods. The function z is approximated by function b, which depends on some values zjk, which are the values of the proximate solution at the collocation points. In the two-step collocation methods, the solution depends also on some values of the solution in the previous time interval. But essentially, since those informations are already known, we have still to compute only m unknowns in the time interval tj minus 1 tj. And how we do that in the usual way of the collocation, we impose that the solution verifies the fractional differential equation at the collocation points, which are the points tj, k. And so we come to a nonlinear system of dimension n to be solved at each time interval. And the same computational cost is required both for the one-step and two-step collocation methods. So they have the same computational cost, apart from a starting procedure, which is necessary for the two-step collocation methods. Of course, to obtain a computational form of the nonlinear system B, we have to compute the fractional integral of function b. And this is equal to this formula. And so we have to compute the fractional integrals of Lagrange polynomials. This can be done analytically, so without any approximation error, once we know the coefficients of the Lagrange polynomials with respect to the canonical polynomial basis. And this, to avoid the van der Waals systems, we adopted the convolution, we applied the convolution, and we could easily obtain such coefficients. Similar observations can be drawn also for the two-step collocation methods. The formula is a bit more complicated, but the remarks are the same. But how it was very well said and it's illustrated by Professor Steins this morning, one of the key ingredients to obtain high order of convergence, also for the spline collocation methods, is the use of a graded mesh. That is a mesh which is not uniform, and in particular, when R is greater than 1, most points are crowded around the origin, which is the part where the solution is less smooth. And so, under this hypothesis of a grading exponent, and by studying the convergence in a Banach space CQ-ME, which is a subset of the continuous function on 0t, where we also illustrate the behavior of the derivatives of the solution, we can study the convergence. We know, I will skip the details, the conditions under which the solution belongs to this space, and under the same hypothesis, we are able to prove the convergence of the method and to obtain a bound for the error. And as you see, we have three different bounds independent on the values of the grading exponent R. Of course, the best case, so the fastest error decay, can be reached by in the third case. In this case, we have that the order of convergence for the one-step collocation methods is m, and of the two-step collocation methods is 2m. In the case of Gaussian collocation points, we have also a super convergence result for the one-step collocation methods, but in any case, they are not, the order of convergence is not greater than the order of convergence of two-step collocation methods. And now I will illustrate some numerical examples to compare those two classes of methods. I will consider some nonlinear problems, and the first case is the easier one because the solution is very smooth. In the second case, the solution is C1 but not C2, while in the third case, the solution is just C0 but not C1 around the origin. And now we compared the computational cost, the number of function evaluations, versus the number of correct digits. We compared one and two-step collocation methods of the same order p equals 4, and moreover, one and two-step collocation methods with the same number of collocation parameters, and so theoretically with the same computational cost. In all the cases, the best performances were obtained by the two-step collocation methods. Similar results were obtained with 3 collocation parameters, except for the fact that for the problem 1 and 2 that were the easier problems, when low tolerances are required, the best performances were obtained by the one-step collocation methods. And more recently, we devoted our attention to the study of the numerical stability of those class of methods. And so we considered the basic test equation in the context of fractional differential equations. The solution vanishes at infinity when lambda, the parameter lambda, belongs to the set sigma alpha. And so we are looking for conditions to impose to numerical methods to obtain a similar behavior from the numerical approximation. So we applied the one and two-step collocation methods to this equation, and we found these recurrence relations. Their expression is similar. The difference is that the matrices W, Wj are of dimension n in the case of one-step methods, and of dimension 2m in the case of the two-step collocation methods. To study, as it can be seen, they are difference equations of unbounded order, and so we do not know the solution in a closed form, and so we have to use some more sophisticated tools to derive some stability conditions, as for example, the form of power series. With this mathematical machinery, we were able to find, to characterize the regions of stability. And we found that in both cases, the region of stability can be characterized in terms of the power series W of C over gamma of alpha, where W of C is a formal power series of the function of the matrices Wj. And so by this theorem, we could construct some regions of stability. Here I did just some examples. On the left, we see some bounded stability regions for the one-step and two-step collocation methods. As we expected, in some sense, from the multi-value methods, the regions of stability are smaller. A similar observation can be done for the right figures. In those cases, the regions of stability are unbounded because we have to consider the regions outside those boundaries. And even in this case, the regions of stability are smaller for the two-step methods, but they are, in any case, A alpha, P alpha stable, which is the analogous of A stable methods for ODs. So, and so one thing that I did not underline was that when we applied the numerical method to the basic test equation, we adopted a constant step size. But we said at the beginning that we apply the spline collocation methods with a graded dimension. So we tried to use the results of the numerical stability also in the context of a graded dimension. And so we imposed that the maximum value of the step size should be less than the within the region of stability that we computed in the constant step size framework. And as a matter of fact, as when H max it is within this region, the no instability arises. While when the H max is greater than is outside that stability region, that some instability arises even later with respect to the constant step size case. And so I illustrated made the convergence, the construction, convergence, and stability analysis of the 1 and 2 step collocation methods, and some future developments are can be done, such for example, to apply those methods to multi-term fractional differential equations, to implement also the 2-step collocation method in an efficient way. That is, we have to adopt a suitable starting procedure, and moreover, we can adopt a fast computational fractional convolution, which is known from the literature, and even to use other bases with respect to the polynomials one. And thank you for your attention.
Thank you, Angela, for the presentation. Are there questions? Please.
I'm sorry, maybe I missed.
Just a moment. Otherwise, they don't hear from the.
Sorry, maybe I missed. You are using the general degree, but which degree?
No, degree M. That is the same in the degree.
And which smoothness?
C-1. That is, we can have some discontinuity points in the mesh points. So the solution is the piecewise solution may have discontinuities at the mesh points.
So it is just so it's a sequence of piecewise polynomials.
Yes, yes.
Just so without any smoothness.
Yes, yes.
Okay. So it's fine.
Oh yes, 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 you're right. Yes, yes, yes. In the literature, they call even in this case spline, but you are right. They are no.
The pieces in one interval and the next interval are basically not related because they are.
Oh, actually, because they. No, you're right. Yes, because we remove. Yes, yes. We don't require. Yes, we don't require that it is a continuity in the between two intervals. Yes.
And did you experience in practice any difference between even and not degrees?
But not really. No, I guess no. But I have to be sincere. We don't use the more than 4 collocation parameters. So maybe some further numerical experiments should be done to verify what you are suggesting. Thank you for your remark.
Other questions from chat? Is there something? Okay, so I will like to thank Angela and all the speakers of the panel. Stop now for 2 hours, so we will start again at 2:30, and there will be the young talk blitz in which the young researchers that are here will present their ideas and projects. And so it's an important moment also to share ideas and references. So please stay with us for you present and for you at home. Thank you again. See you later.